Welcome to The Explainer. Today, we're going to break down the science of gas mixtures. Now, this is a topic that's not just all around us. It's literally in us with every single breath we take. And as you'll see, understanding how gases mix has some surprisingly deep and powerful implications for everything from engineering to the fundamental laws of nature itself. So let's just start with this question. You breathe it every second of every day, but what is air? It feels like it's one single thing, right? But it's not. It's a mix, a cocktail of different gases, mostly nitrogen and oxygen, all just kind of hanging out in the same space. And getting a good handle on this everyday mixture, well, that's our first step to understanding some much more complex and powerful systems. So here's where we're headed today. We're going to start with the basics. How do you even write the recipe for a gas mixture? From there, we'll look at the simple rules for so-called ideal gases before we see what happens when things get real. Then we'll figure out how a mixture's properties are really just the sum of its parts, and we'll wrap up with a pretty mind-bending look at the cost and the hidden energy of unmixing. All right, first things first. If you want to understand any mixture, you gotta know its recipe. And in science and engineering, there are really two main ways to write that recipe down. You can either go by weight, or you can go by a straight-up count of the molecules. Okay, the first way is called mass fraction, and it's pretty much exactly what it sounds like. You just take your container of mixed gases and you ask, what percentage of the total weight does each gas make up? It's just like a recipe that calls for, say, 2 kilograms of this and 5 kilograms of that. Simple as that. Now, the second way, and this is often way more useful for chemists and engineers, is the mole fraction. So instead of weighing the ingredients, we are counting them. See, a mole is just a standard number we use for counting molecules, kind of like how a dozen always means 12. So the mole fraction tells us, hey, what percentage of the total number of molecules in here belongs to this one particular gas? Okay, so now we know how to describe the mix. The next question is, how do we predict what it's going to do? Well, for a lot of common situations, we can actually use a simplified set of rules, a playbook, if you will, for what we call an ideal gas. And the main idea here is really simple. Just imagine that all the little gas molecules are so incredibly far apart that they basically ignore each other. They're like tiny little billiard balls zipping around that never, ever get close enough to attract or repel one another. It's a huge simplification, but this one assumption gives us a surprisingly powerful and simple way to predict how the whole mixture will behave. This simple idea leads to two really foundational laws. You've got Dalton's law, which says the total pressure is just what you get when you add up each gas's individual pressure. Then there's Amagat's law, which says the exact same thing but for volume. But here's the really cool part. For these ideal gases, these two laws aren't really different. They're just two sides of the same coin. And that right there, that gives us this absolutely beautiful shortcut. For any ideal gas mixture, the mole fraction, the percentage of molecules, is the exact same as its share of the total pressure and its share of the total volume. So if oxygen makes up 21% of the molecules in the air, you know right away it's also responsible for 21% of the pressure. It's a super convenient rule of thumb. But you knew there was a but coming, right? The real world isn't always so neat and ideal. That simple playbook works great when pressures are low, but as soon as you start to really squeeze those gases together, well, that's when our simple rules start to break down. And this quote from a classic textbook really just nails it. You see, at really high pressures, those molecules are forced incredibly close to each other. And all of a sudden, those tiny forces of attraction and repulsion that we were ignoring, they're not so tiny anymore. They start to matter a lot. And trying to use our ideal rules in that situation can lead to huge, unacceptable, and frankly, dangerous errors. And here is exactly what that error looks like in the real world. For this particular high-pressure mix, the simple ideal gas law says you need a tank that's 1.33 cubic meters. But look at the more accurate methods below it. The real volume needed is less than half that size. An error of over 100%. In engineering, that's not just a small oops. That's a potential catastrophe. Okay, so if the easy way is dead wrong, How on earth do engineers get the right answers when they're dealing with these real gas mixtures? Well, one of the most popular tricks is a method called K's rule. It's pretty clever, actually. Instead of trying to juggle all the different gases in the mix, you first calculate some pseudo or kind of fake average properties for the whole thing. You basically pretend the entire mixture is just one single substance. Then you use those fake properties to look up a special correction factor, and you just multiply that correction into the original ideal gas equation. It's a fantastic way to get a much, much more accurate answer. All right, so now we can predict a mixture's state, its pressure, its volume, its temperature. The next logical step is to figure out its properties, like, how much total energy is actually stored inside. And the way we do this is pretty intuitive. For total properties, like the total energy inside the container, you just add up the energy of each individual gas. Piece of cake. But for properties that describe the character of the gas, like its specific heat, which is how much energy it takes to raise its temperature by 1 degree, for those, you calculate a weighted average based on how much of each ingredient is in the mix. And why do we go through all this trouble? Because these sum of the parts calculations, this is exactly how engineers design the machines that power our world. It's how you figure out the power output of a jet engine, or how much heat you need to pump into a giant chemical reactor. It's fundamental. And that brings us to our final section. And this is where all these ideas come together into something really profound about energy and the nature of the universe itself. We've talked a lot about how gases mix, but what does it take to unmix them? You know this from your everyday life. You pour cream into your coffee, and it mixes all by itself. But have you ever seen the cream just decide to separate itself back out? No way. It's a fundamental law of nature. Things always move from a state of order toward disorder. It is a one-way street. You will never, ever walk into a room and find that all the oxygen has decided to hang out in one corner while the nitrogen chills in the other. It just doesn't happen. So, since mixing just happens spontaneously, going the other way, unmixing something, always has a cost. It takes work, it takes energy, and thermodynamics actually lets us calculate the absolute rock bottom minimum amount of energy that's required. It's the price you have to pay to reverse a natural process. And believe me, this isn't just theory. Just look at a massive industrial process like desalination. Seawater is just a mixture of salt and water. And the immense amount of energy that those plants have to use, that is the real-world cost of fighting nature and forcing that mixture back apart into pure water and salty brine. But hold on, this whole idea has an absolutely incredible flip side. If it costs energy to separate a mixture, that must mean that mixing it releases energy. And the amount of energy we're talking about is just staggering. Look at this number. That's the potential power we could generate just by harnessing the energy of one single major river mixing with the ocean. That's a city's worth of power, happening naturally all the time. And that's the final thought I want to leave you with. That simple, everyday process of things mixing together, it's releasing vast amounts of energy all around us every single day. And we're just ignoring almost all of it. It really makes you wonder, what other huge free sources of energy are just hiding there in plain sight, waiting for us to get clever enough to tap into them?